So who wants to go first? Okay, you're talking about the Sun Lab? Okay. Um, yeah, I think I have a slide that I have already annotated. Let me see if I can load it up, if I can find it. Oh, okay, date 1. That's now I remember that's part of the rotation. Let me open that page. Maybe I haven't done that yet. We talked about the Sun Lab in a previous session, but I think since that was the session leading up to the Light and Spectra Lab, we only talked about one aspect of it, and I think that was identifying the different layers. Okay, yeah, let me see if I can bring up the slide. I'm going to have to capture it first. Oh, think again. Yeah, let me see if I can get that slide on the whiteboard. Hang on a second. Um, no, wait a minute. Date 1 does show the different features. Okay, I may already have that. Let's see. Oh, I'm clicking the import button, but nothing is happening. Okay, well then let's do it a different way, and I'll share my desktop. Oh, okay, here's an import. Hang on. Let me import the image. Okay. Actually, I'm wondering if this is it. Let's see. Okay, yeah, this is one where it's not annotated, but that's okay. Well, you're looking here at the 4 different atmospheric layers of the sun. I'm not exactly sure if this is date 1 or some other date. Let's see, this might be date 2. Anyway, you can identify the different layers by their characteristics. So on the bottom right here, you see the photosphere. Let me just type that in with a box. Okay, and I'm going to pick a light pen color. Okay. The photosphere is also abbreviated as pH once you write it into the lab. And the main features in the photosphere are the tiny little sunspots here. And essentially the photosphere is the layer that we see in the visible light when we look just through a visible telescope with our eyes. So that's how we see the sun. So let me just circle one of those little sunspots. Well, here are a bunch of little sunspots. So that would be one characteristic feature of the photosphere. And also the photos. Say again? Do you want to just go ahead and type? Okay. Yeah, let me just keep going. Just yeah, you can type at any point, and then I'll see it come up. Okay, another feature of the photosphere is that it has a very smooth texture. And you can see when you look at it that there's really not as much graininess, or it's not as dynamic as on the other layers. Oops. I was just going to type something, but then it ran into something else. So okay, maybe the yellow is kind of hard to read. Okay, so smooth texture. Also, what you can see in the photosphere is the limb darkening. So that means the limb is essentially the outer edge, if we think of looking at the sun as a disk. So if we go to the outer edge of the sun's disk in the sky, it appears a little bit darker than the center. You know, if you look here at the center, it is brighter, and then if you go towards the edge, then it's darker. So that's generally what's called limb darkening. And I'm going to change my pen color so it's easier to see. Okay, I'm trying to make an arrow here. And add the words limb. Just have to make sure I spell it correctly. It's limb darkening. Okay, so it becomes darker along the edges. So that's essentially the photosphere. Oh, okay, Lenita typed a question. Hey, is there supposed to be something on the screen? Yes, we're looking at an image right now. I hope everybody else can see it. It's supposed to be one of the composite images, one of the date images in the Sun Lab, where you see the 4 different layers of the Sun's atmosphere. And we were just talking about the image on the lower right, which is the photosphere. So that's easy to recognize because it is the smoothest layer, and the only things you can see on it are tiny little black dots, which are the sunspots. Another layer that's easy to identify is the corona, which is on the bottom left. I'm going to label that.
I'm sorry, Professor LaHaye. This is Mardina, and I'm in here twice because the other screen is up on me and I can't get it out. But I can't see anything but that you typed in photosphere.
Okay, you said you can't see anything. Yeah, maybe you can log in or log off and try again, just like what Lenita is trying to do. I don't know if I can get you out or not.
Okay, I'm going to have to probably reboot my computer. I'll be right back.
Okay. Joanne, can you see the screen? Can you see the different layers of the solar atmosphere? Oh, okay.
I can see.
Well, while we're waiting for Medina to get back in, do you have any questions?
You hear me?
Yes, yes.
Okay. One of the I think in assignment 4 was asked about the
Joanne,
chord.
you're cutting. Wait a minute. You're cutting in and out again. So I get every other syllable when you speak. Oh, okay. Well, we can just type.
What number would have to go in?
Martina, have you gone through the setup wizard for the Wimba? See, I'm trying to get out of the e-board, but apparently once I'm in, I can't get back out. Okay, I just clicked on the e-board button again. Okay, it cleared the e-board now. Oh, except... Oh.
I only where it's
Say again? Okay, I've just imported it. Oh, okay. Yeah, maybe it was because you had logged in and something wasn't working and I imported the image, and then because it wasn't working you couldn't see it, and then you logged in again, and because you were already logged in, it might have been one of those Wimba computer things. But anyway, well, I'm glad we could all see the image. Okay, so this is an image that is similar to one of the date pictures. And in those images, date 1 through date 5, you're supposed to identify the different layers. You know, just label which layer you're looking at and what part of the image. And then I think that's all you have to do. And also identify, yeah, there's a top left image. What features, what active regions are similarly placed in the other pictures. Well, let me just go through and identify those for you. I think we started with the bottom right image, which is the photosphere, and I labeled it. And this time I can pick a pen color that is visible both on black and on white. Okay, so the bottom right image is the photosphere, and later on, when you go to the end of the lab, you'll also need to identify different features on each layer that are unique for each layer. And in the photosphere, what's unique about the photosphere is that it has these tiny little sunspots. And when we look at the sun in the visible light, then that's also what we see, the sun, what it is like. You know, we see the photosphere. So those tiny little black dots on it are the sunspots. I'm going to label those. So they're distinct for the photosphere. And generally, the photosphere is the smoothest looking layer of the sun. So I'm just going to put something like smooth texture here to indicate that, you know, that's one of the unique features of the photosphere. Another feature that is sometimes quoted is that at the edge, when we go, you know, from the center where it's very bright, we go to the edge, that it gets darker, so that to the edge of the disk that we can see. So I'm going to put an arrow there. And just refer to that as limb darkening. Okay, so here's the arrow. And we switch back to the text. Okay, so that would be the limb darkening, which we see only on the photosphere. On the other ones, it's not, the limb darkening is not so apparent. By the way, when you enter how you identify the layers in the lab assessment, you can abbreviate the photosphere with pH. So I'm just going to write that here also. Okay, so photosphere equals pH. So you don't have to write that whole word every time. Okay, and then here on the bottom left image, that's another one that you can identify really easily. This is the corona. That's the outermost layer of the solar atmosphere. And it's actually very thin, but it's also very hot. So the corona is the most dynamic looking layer, and it's generally sort of dark, and then with these white splotches, and those are actually magnetic loops of a magnetic field, and they're also referred to as coronal loops. Well, let me just label the layer. Okay, corona, and you can abbreviate that as CO. And then we have the very dynamic looking coronal loops. So those would be the coronal loops. And essentially you have charged particles that are racing along the magnetic field lines of the sun. And you also have coronal holes, which would be the exact opposite. They would be the darkest splotches. Right, here's one, for example. And there's not much going on in those coronal holes. So this is where there's very little activity. So those would be the coronal holes. And those two features are unique to the corona. And the corona is, again, easily identifiable because it looks the most violent and the most dynamic. And it has, the highest contrast in the features. Okay, and then if we go to the upper left image, that's the lower chromosphere. and you can abbreviate that as LC. And what you can best see is that it has sort of a grainy texture, an overall grainy texture. And that overall grainy texture is actually called granulation. And that's pretty much all over. Yeah, and the granulation, you can see it a little bit, well, in the photosphere, but not very much. That's due to the energy that is coming up from directly underneath the solar atmosphere, and sort of like, bubbling water. Those are convection cells, where you have the hot material rising from underneath and then cooling off at the top and sinking back down because it's cooler and more dense again. And that is repeating over and over because you have all this energy coming up from underneath the surface of the sun. Okay, but then besides the granulation, the other feature that you have in the lower chromosphere would be the plages. And those are those white splotches. So that would be a plage, singular, or plages, plural. I'm just going to write plage right here. And of course, there are several more sort of down below that one in the center. Yeah, so that's pretty much it for the lower chromosphere. It's not very distinct looking otherwise. And the lower chromosphere, and on the right upper part, we have the upper chromosphere. And that is labeled as UC, or abbreviated as UC. And it has a smoother texture than the lower chromosphere. And overall, it also has the plages, but they're not quite as pronounced. So let me just circle one of those plages here. So we also have this plage. But something that the upper chromosphere has that the lower chromosphere doesn't are these dark splotches here. I'm going to maybe circle them with a different color. Yeah, this particular image of the upper chromosphere is actually not a very good example of those dark splotches or those dark streaks. You'll see when you go through the date images that there are images of the upper chromosphere in there where you can see them a lot better. Okay, and those dark streaks are called filaments. And those filaments you can only see on the upper chromosphere. You don't see them in the lower chromosphere. Yeah, so in general, those two are the hardest to distinguish, and people get those two confused the most, the lower and the upper chromosphere. But yeah, remember, the lower chromosphere always looks more grainy, and the upper chromosphere has these dark streaks, those filaments, that the chromosphere doesn't have. So that's how you can distinguish the two from one another. In addition to identifying the 4 different layers, the manual also wants you to, if you look at the upper left image, you have areas of activity. And I'll do that in a different color. or you have active regions. So let me make blue arrows for those. Oops. So the plages here, for example, that would be those would be the active regions. Actually, I didn't want that. Oh, dang. Now everything vanished. I just wanted to shoot. Well, I have the labeled image somewhere, so I'll see if I can dig that back up and post it when yeah, an email or on the bulletin board. Yeah, let me just talk about the active regions then. So that is the last part of this identifying the date images. Okay, so this plage would be an active region. See, here we have more plages. Okay, let me just label those as active regions. Okay, and then the question is, compared to the image on the upper left, which would be the lower chromosphere here. So I can just quickly add that back in. Then the question is, which of the other images shows activity in exactly the same regions? So that means only one of these other three images was taken on the same day at the same time as the image on the upper left, which in our case would be the lower chromosphere. Actually, if you look over to the right, upper right, to the upper chromosphere, you can sort of see the active regions in the same place. So it has a plage right here. Oop, gotta switch it back to the pen. Yeah, that almost has the same texture or the same indentation as the plage on the lower chromosphere on the left, on the upper left. Yeah, and then you have these three main areas of activity. So the upper chromosphere really matches the best in terms of where it shows activity compared to the lower chromosphere on the left. Okay, are you sort of clear on this now? On the date 1 through 5? Or do you have more questions about it?
No, I just thinking.
Okay. Well, while we're at it, shall we also talk about the rotation? Because that's usually the hardest part. Okay. Yeah, I'll try to upload another image real quick that I need to capture first. So just bear with me for a little bit. Okay, just gonna go back. Okay, I'm almost ready to bring it in. See, Wimber's a little bit slow for me at the moment. So you're just trying to maximize the window. It's frozen. Oh, okay, here we go. Okay, I'm trying to import the image now. Okay, here it is. So can you see the new image? Yeah, this is the rotation 1 image. Yeah, so that would be the composite image on page 15.9 in the lab manual. And it shows basically 9 sub-images. So starting with the one on the top left, that one was made September 1st, 1994. So let me just put in here, let me do this in red again. So this was taken September 1st. And yeah, these images are taken in succession, not one every day, but maybe one every 2 days or 3 days. Of course, you know, the first three across the top here, they are taken every day. So this one would be September. Make that a little bit higher. September 2nd. Then September 3rd. Okay, now in the middle row, it's September 5th, 6th, and 7th. September 5th. September 6th. September 7th. And then in the bottom row, it's September 8th, 9th, and 10th. Okay, September 8th, September 9th, September 10th. Okay, and the idea is to measure the rotation rate of the sun. And we're going to use one of the coronal loops as a landmark and track that from one day to the next across how it changes position across the face of the sun. So since we're looking at, you know, one half of the sun, if we can figure out how long it takes to move halfway across from the left side to the right side, then we could just double the time, and that'll be our full rotation period. So, yeah, so we're looking at the corona, and yeah, we can just pick one day where we start with the best thing would be to pick a feature that is just coming around the edge. And if it's like plus minus within a day or two, you know, that's okay. Well, there's a feature that is coming around the edge, around the left edge, you know, the 9 o'clock position. Okay, so yeah, Martina, you're asking for image 1, the plages at the edge. Actually, what we're looking at here are our coronal loops. So we're looking at the corona, and those white things are coronal loops. Yeah, we have 2 of them right here. And we just sort of have to decide which one we want to track, and is it coming, you know, which one is coming around the edge. So there'd be one, and there's actually another one at the very edge right here. Yeah, those are not very pretty arrows. Okay, so those are the coronal loops. I guess I would be inclined to go to the second picture and start, you know, use that as the starting date for the coronal loop that is at the very left here. I'm going to circle it. Okay, so we're going to start tracking this coronal loop on the very left. Ooh, that was not very good. I don't know. What did I just do? Oh. Ah, I found the undo button. Okay. Okay, so we're going to track this loop. And right now it is coming around the edge, and there's a blank. If you look at page 1510, you need to fill in a couple of blanks here. The first one is feature, so that would be a coronal loop. And then the second blank would be the left limb beginning location. So left limb just means the left edge. And with a location, we're going to use the clock face. Yeah, let me put the clock face on the first image just so you can sort of see. I'm just eyeballing here the center. So just about here. So this would be the center point. And then we have, let's see, yeah. So up top would be noon. Here on the right side would be the 3 o'clock. On the very bottom, the 9 o'clock. And then on the very left, bottom 6 o'clock. And then on the very left, the 9 o'clock. So let me just write that in. This would be 12 o'clock. This would be 3. Then on the bottom, 6. Let's see, yeah, it's a little bit high. 6, and then over here we would have 9 o'clock. Okay, then of course, you can imagine all the other numbers in between. So 1 is about here, 2 is about here, 4, 5, 7, 8, and then 10, 11. So that would be the clock phase. And that's how we express in which direction it is. But then technically we would also have to express how far away it is located from the center. And we would do that as a fraction of the radius. So if it's all the way at the edge, we would just say 1. And if it's all the way at the center, we would say 0. And let's say if it is halfway, then we would say 0.5. If it's 3/4 of the way, it would be 0.75. And if it's all the way at the edge, again, then it would be 1. And since we're tracking the coronal loop at the very left edge of the limb, we would say, I'm going to mark that on the second image now. So you put the center point in here again. Okay, and then so where the coronal loop is would be at a distance of 1 away from the center, so 1 radius, and the direction would be 9 o'clock. So let me write that out here. It would be, or you could say 9 o'clock and then 1 for the radius. That would be the position of the feature. Of course, you can't really see the 9 now. So that's what you would put in the left limb beginning location, blank, on page 1510. And then in the date field, you would put September 2nd. Okay, so we have the starting date. Yeah, this here would be the starting position. Okay, so then we'll track it until it disappears on the right edge. So I'm just going to keep putting circles around it. So on September 3rd, it has moved a little bit further around the edge. Then December 5th, oops, that one was a little bit large. Let me just undo this. So it's coming more and more around the face of the sun. Okay, on September 9th, it's pretty much in the middle. So you could almost say that between September 2nd, where it started coming around the left edge, and September 9th, where it is in the middle of the face, it has gone a quarter of the way around the sun. So that could be like a quarter of the rotation period. Of course, we don't really have to write this down, but just as an estimate, so if we subtract the number of days, 9 minus 2, we get about 7 days. So if 7 days is a quarter of the rotation period, then half a rotation period should be around 14 days, and a full rotation period should be about 28 days. So let's see if we come up with that. But we see that by the time we get to the bottom right image, the last image, it hasn't really gone all the way to the right edge and about vanished there. So that means we actually have to go to the rotation 2 image now, where the bottom right September 10th date is actually repeated as the top left starting date of the rotation 2 image. Okay, let me just label the bottom of this image rotation 1, because I'm going to save it and then I need to know, what I'm looking at. Okay, so this is overall the rotation 1. Okay, I'm going to save this snapshot. Okay, and now I'm going to get the rotation 2 image. Just bear with me. Okay, Okay, almost there. Oops, clicked on the wrong one. Okay, now we're almost there. Okay. Well, while we're at it, let me go ahead and save the last one, rotation 3 too. 3 also. Okay. So I'm going to have the images now, and then now I'm going to import them into the whiteboard. First, rotation 2. Okay, it should be coming up shortly. See, can you see it? Oh, okay, great. Okay, so yeah, let me put in the dates again. Okay, so the top left image here, sub-image, is the same as the last image of the previous set. So this would be September 10th. Then the next one is September 12th. Okay, then we have September 13th. September 16th. '17th. September 18th. No, that's actually 19th. Didn't pay attention. Okay, here we go. Okay, put the 19 in here. Okay, then 20th, 21st, and 22nd. Okay, and let me label our coronal loop again, the one we're keeping track of. Oops, it was a little bit anemic. Okay, so here's our coronal loop. And it keeps moving further and further to the right edge. And actually we have a break here between September 13th and September 16th. It has already moved almost out of view. We can see like a little bit here still at the top, but essentially, you know, it's basically already just around the edge, just around the right edge. So maybe I should note that. So the loop has just gone around the right limb, and that's September 16th. So you probably want to put down, if you go back to the blanks on the rotation page, that was page 1510 in the lab manual, the right limb disappearance location would be, well, 1 for the radius because it's at the edge, and it would be 3 p.m. or 3 o'clock, doesn't care if it's a.m. or p.m., so it would be 3 o'clock as a disappearing location. And for the date, you probably want to put something like maybe September 15th rather than September 16th. Because then it wouldn't be quite so far around the right edge yet. So let me put the location, would be 3 o'clock and 1. So I put that down here. And you would probably estimate, I'm going to write that down too, maybe in light blue or teal. So you estimate September 15th as disappearing date, because it's already a little bit too far around the edge here. Well, and if you look back, I think we had September 2nd as a starting date, so then September 15th as a disappearing date. That's a difference of 13 days. So that's just about the estimate that we were getting from tracking the feature a quarter way around. Okay, so now the time from the appearance around the left limb on September 2nd and the disappearance on the right limb on September 16th, that difference in dates, well, actually 15th, that's what we had estimated. So 13 days, if we double that, that would give us an estimated full rotation period of 26 days. Because, if it takes 13 days to go halfway around the sun, then it should take 26 days to go all the way around the sun. So then we would, this estimate, 13 days, goes into the difference between the dates, blank, which is about half the rotation period. So then we want to check, okay, 26 days after September 2nd. September 2nd plus 26 days, that would make it September 28th. So then, of course, the last image on our rotation 2 slide here has the date of September 22nd. So that means we'd have to go to rotation 3, to the rotation 3 image, in order to see if our feature comes back around on September 28th. So let's quickly go and do that. Let me just label this image as rotation 2 and save it real quick. Yeah, I'm going to have to go soon and get my kids to bed. But yeah, let's just finish up the rotation here. And I'm going to import okay. since I've already gone and saved that, it should go a lot quicker now. Okay. Okay, so do you all see the new image? Okay, cool. I'm going to quickly go through and put in the dates. Okay, so we have September 23 on the top left. Then September 24, top middle. September 26, top right. Okay, September 27. September 28. September 30. Oops, it's actually September 29. Was ahead of myself again. Okay. September 30. Oh, and then it switches to October 2nd, and October 3rd. Okay, well, we had predicted that starting on September 2nd, and then it vanished around the right edge September 15th, so there was a 13-day for half a rotation period, which means that the full rotation period should be 26 days, and starting on September 2nd, if we add 26 days to that, that would bring us to September 28th, which is the center picture. Now, remember if we look back to rotation 1, there were two features, two loops that were really close by each other that both came around the edge. And we tracked the one that was coming right around the edge that hadn't fully appeared around the edge yet. So it looks like in September 28th, that our feature is still a little bit behind the left limb. So I'm going to make a little arrow there. Okay, so our loop is just behind the left limb. And I think when we started tracking it on September 2nd, it was already a little bit further around. So, if we go to September 29th, that looks a little bit closer to, what the image on September 2nd looked like. So on September 29th, we could say, that it is coming back around. And of course, the reappearance location, so we would note September 29th as our reappearance date, or the reappearance location. We would again put that as 9 o'clock, and it's exactly at 1 full radius. So the location here again would be at 9 o'clock and a radius of 1. So that would be the reappearance. Kind of a tough word to spell. Okay. Okay. And then if you subtract the September 29th minus September 2nd, then you get about 27 days as a rotation period for the sun. Okay. Are there any other questions about this lab? Let me save that image.
I don't.
Okay. Well, you're very welcome. And let me just type the rest. And if you have any questions, email them to me anytime or post them to the discussion board, and I'll try to get them as soon as possible. I'm also going to go ahead and, I don't know if I'll make it later tonight, but definitely by tomorrow I'm going to post those annotated images that I made. Okay, well, I'm going to sign off then and bring my kids to bed. Good night. And see you next time.
Thanks, and good night, everybody.
Okay, good night, everybody.